Hi. In the previous video, we've actually derived a formula for finding the time path for first order differential equation with variable coefficient and variable term. And look, now we're going to see the application of what we learned into very, very important differential equation that you see over here. Look, dy dt plus ay equals to beta 2 t plus beta 1. Look, this is actually a hybrid because look, here we have constant coefficient, but what variable term? Well, unfortunately, in order to solve it, we still need to use the formula because we don't know something called method of undetermined coefficient that we're going to learn about later. So, why is this equation so important? Because look, I don't want to share too many details from the beginning because we need to solve it to get actually how it works. Look, this equation is very good at modeling economic variables, especially GDP. So we're going to assume that our y is GDP, and GDP is governed by this differential equation. And look, from this equation we will get both equilibrium level of GDP, that is actually should be changing over time because, you know, economies are growing over time, but we will have also some dynamics coming from the derivative. But how this will all get together, we'll see once we solve this equation. But look, let's introduce some assumptions. Look, we are assuming that A is bigger than 0, beta 2 and beta 1 are also bigger than 0, and beta 1 is far greater than beta 2. Why? You will see later. Okay, so let's start solving it. Look, we start by using, of course, the formula we've introduced previously. So we've got that the solution should be given by e to the power negative integral u dt. Let's write it like this. A plus integral w e to the power u dt dt. Okay. Now we can start substituting. Look, A is our u, so we can do it easily. We've got negative integral a dt times a plus integral. Our w is beta 2 t plus beta 1, and this times e to the power integral a dt. And look, some of these components are really easy to calculate. For example, integral of a is at, so we've got a to the power negative at times a plus, well, here let's leave the integral for now, beta 1 t plus beta 2t plus beta 1 times e to the power at dt. And here we are arriving at our, actually the only problem we're going to have. Look, this integral is not very pleasant to solve. We need to resort to integration by parts, but don't worry about it. I'm going to remind you how it is done, and in the future we're going to use the method of undetermined coefficient that will make all the calculations far simpler. Okay, so look, what we need to deal with is that integral. So we've got integral beta 2t plus beta 1 times e to the power at dt. Yeah. And now look, when we use integration by parts, we are assuming that some part of it is called v, the other part is called du. Okay, and we're going to do it in the same way. This is going to be our v times du, and we know from the derivation of the formula we did in mathematics class that this is equal to u times v minus integral v du. Okay, so now what is v, what is u? We said that this first part is going to be v. It doesn't matter in this case. I believe this is just easier that way. Okay, so we've got v, which is beta 2t plus beta 1, and dv, so differential of v is simply derivative of v with respect to time times dt. So derivative of this with respect to time is just beta 2, and times dt, right? This is. Now, in order to get u, we need to work a little bit harder, because u is going to be integral of this expression. And now, look, if I want to integrate this and use exponential rule, I need to have a up front, so I should take 1 over a out of the integral, and we get that this is e to the power at over a plus c. Okay, I will be adding c, but look, later on we will need this. We will not need the c, and as we said, we can get rid out of a lot of these arbitrary constants because they are going into some other arbitrary constants. Okay, now du is equal to derivative of u with respect to time times differential of time, dt. And look, du dt, because here we integrated u, because here to get u we integrated this expression, but this expression must also be derivative du dt times dt. And look, now we see that this is v, this is du. So this is what we wanted. And now we can start substitute to the solution. Okay, we will not need this part anymore. Okay, so we've got that this is beta 2 over, okay, I'm going ahead of myself. Let's do it slowly. Beta 2t plus beta 1 times e to the power at over a. And then we've got minus, I'm sorry, of course here is u dv. So now we put u over here, and if I put u over here, I'm putting here e to the power at over a, and times dv, which is beta 2 dt. Okay, now we continue. So look, I can now rewrite this expression as beta 2 over a t plus beta 1 over a times e to the power at. And now let's deal with this expression. Look, I want to use here exponential rule again. So what I want to take out is definitely beta 2. Okay, so let me write it as beta 2. And I want to have here a. So what I need to take out? A squared. 1 over a squared, I'm sorry. And we get that a times e to the power at dt. And this, of course, is equal to beta 2 over a squared times e to the power at. Okay, so now that we've calculated this integral, we can substitute it over here. Okay, so what are we getting? This is e to the power negative at times a plus. Okay, look, I can put all of those inside the parentheses here, right? Because they all have common part e to the power at. Okay, so we will have beta 1 over a t plus beta 1 over a minus beta 2 over a times e to the power at, and we close brackets. Now look, if I'm going to be multiplying this, if I multiply this by this, I'm going to get the complementary function, a to the power e negative at plus. And now look, if I multiply this by this, they're going to cancel each other out to 1. And we're going to get that this is plus beta 1 over a t plus beta 1 over a minus beta 2. I'm sorry, here should be beta 2. Oh, beta 2. Everywhere was okay. When I was rewriting the result, I made a mistake. Over a square. Okay, and look, this is our solution. It doesn't look very pretty, so let's make it look more pretty. Okay, so let's say that this we're gonna call beta. And this one we're gonna call alpha. Look, beta is definitely positive because both of those are positive. Now, here beta 1, we said, is far greater than beta 2, so we can also be sure that alpha is bigger than 0. So look, the equation that we finally got has the form, so the time path of GDP is given by a e to the power negative at plus beta t plus alpha. Okay, and look, this is the equation that is giving us the time path of GDP. So, what is this telling us? Okay, so look, maybe let's put this equation on a graph. Okay, so how would we start? Well, first, let's start with particular integral. Equilibrium solution. Look, what you see over here is moving equilibrium. If here we've got GDP, and here we have time, then how do I put this equation? Here I put alpha. Now, we know that alpha is positive, and what is alpha? Alpha is the GDP at the very beginning, at time 0. And then what happens? Then it increases at the constant rate beta. So look, this is equilibrium GDP. We see that it is characterized by linear time trend. And look, this is a very good description of reality. Usually, GDP is characterized by nearly linear time trend over very long time horizons. Okay, now, what about the other part? Our complementary function. Look, this is telling us what happens to GDP if it's thrown out of the equilibrium. Now, do we have convergence here? Well, of course we do. How do we know this? Look, if I'm going to calculate limit with t approaching infinity out of a to the power e negative at, look what happens. If a, we know that a is positive, right? So we here, because we have minus, we are dividing a by e to the power of a t. So look, as t gets bigger and bigger and bigger and bigger, this expression gets smaller and smaller and smaller and smaller. It goes to 0. So look, here we have a process in which if GDP is thrown out of the equilibrium, economy should eventually go back. So look, let's just say that at time t0, there was some negative shock to the economy, and as a result, GDP dropped to this level. Now, what will happen later? We see that from this complementary function, we see that value of the actual value of the GDP should go back to its trend value over time. So we will see that the economy is going back to equilibrium. Maybe let's make this into a dashed line. This is just drop. It's like imagine that GDP was going exactly with trend and then it dropped for some reason. Let's just COVID would be a perfect example, right? COVID happened, GDP dropped, and now economy is adjusting, and GDP goes back to its original time chart. So look, if I would like to draw now how actually GDP is behaving, we would see it like that. And eventually, it's almost covering the same trend line. Okay, and look, so we see that it doesn't matter whether the shock is positive or negative, we will get, the economy is going to come back to equilibrium eventually. But, look now, there is an issue with this. You've probably seen in macroeconomics class or in econometrics class, like how the graph of GDP looks like. And it usually looks like this. Okay, so it definitely doesn't look like what I've just drawn. Okay, but look, you're 100% right. But remember a couple of things. First, we just showed one shot. Look, still, if I would draw a straight line over here, we see that that would be a good approximation of the trend, but there's a lot of volatility here in comparison to my graph. Okay, but imagine a couple of things. First, let's just say that these shocks happen more often. How will this process look like? Look, if shocks are happening more often, it will go like this. Let's just say that GDP goes along the trend line and then drops because of some shock. Something bad happened. And now look, economy starts to go back to equilibrium, but then another shock happens before the economy reached equilibrium. And then, over here, reverse is happening, right? If now we would have a positive shock, the economy would actually jump over here. It would start going back, but then we could have another negative shock. Okay, and I hope you can see that this starts to look more like this. But where are those shocks coming from? Well, it's really hard to answer this question, briefly especially. But in economics, and especially in statistics and econometrics, we make a certain assumptions that describe the reality very, very well. Imagine that we've got normal distribution of shocks. Look, the mean value of the shock would be 0. There would be some constant standard deviation. And imagine it like this, that sometimes there's a negative shock, sometimes there's a positive shock. And look, probability of a shock, look, this, on here you can think about, on this axis, we've got intensity of the shock, or size of the shock. And look, shocks can be either positive when something good happens, or can be negative when something bad happens. Here we have the distribution of probability. And look, the most probable shocks are very tiny shocks that actually concentrate somewhere around the trend. So those would be like some minor events. Now, bigger shocks, positive, like big, very strong positive shocks, are, let's just say, over here. Well, very strong negative shocks are over here. So look, those shocks happen relatively not often. Those are the ones that dominate. And look, if we combine those two things, and so we will be assuming that at each moment there is some shock, like each day, for example, there is some different shock to the economy. Sometimes positive, sometimes negative. On average, they cancel each other out. Now, some of those shocks are, most of those shocks are rather tiny, but just some of these shocks are either very bad or very good for the economy. We will get a graph that looks exactly like this. And actually, I'm going to, part of you, because I know that, I hope that you know that over next semester you are having electives. So you are picking subjects you want to have. If you're going to choose my subject, which is called Advanced Quantitative Economics, well, the material I'm doing in there is pretty complicated, but the exam is very easy, so I strongly encourage you to join the class. I will actually show you a mathematical simulation of how process very close to this one can generate a simple process like this that you see over here can generate a cyclical fluctuation in the economy. But for that we're going to use something called difference equations, not differential equations, which is, look, if you understand how differential equation works, understanding difference equations is like this. It's like just moving from one card to the other. Okay, so this is it about modeling GDP. In the next video, we will learn about different types of differential equations, nonlinear differential equations. See you in the next video.